afternoon to one and all present here. So let us begin today's webinar, the national webinar on few graph concepts and their chemical applications, which is organized by the Department of Mathematics and Research Center of Nesamony Memorial Christian College, Marthandam. So before we begin today's session, let me just brief you the schedule of the program. So we begin with a welcome note by Dr. A. Pramila Inbarose, the head of the Department of Mathematics, followed by a presidential address by our principal. Then we have a felicitation by our correspondent, Advocate L. Rajadure. Then we'll have the first session by Dr. J. John. And after the first session, we'll have the second session, where we have the speaker, Dr. J. Basker Babujee. Then we'll have the interaction session, and then it will be concluded by vote of thanks by the organizing secretary and the head of the Research Center of Mathematics, Dr. A. Vijay. So this is the program schedule. So now let me invite the head of the Department of Mathematics, Dr. A. Pramila Inbarose, to welcome the gathering. Madam, you are not audible.
Respected correspondent of our college, respected of our college, honorable chief guest of this program, professors from various colleges, and my dear students, good afternoon to you all. I happily welcome all of you to the webinar, Few Graph Concepts, and are in this most humble and prestigious occasion. I feel privileged to extend my warm welcome to our principal, Dr. K. Paul Raj, whose energy, enthusiasm, and focus on education and learning helps our institution to achieve greater excellence. A hearty welcome to you, sir. Our honorable chief guest, Dr. J. John, Associate Professor and Head of the Department of Mathematics, Govt College of Engineering, Tirunelveli, has made a powerful contribution in the area. A warm welcome to you, sir. Our esteemed chief guest, Dr. J. Basker Babujee, Associate Professor, Department of Mathematics, MIT, Anna University, Chennai, is an expert in the graph theory area, especially in graph labeling, chemical graph theory, and automata theory. I consider it as a great honor to welcome you, sir. I express my deep sense of gratitude to the organizing secretary and head of the Research Center of Mathematics of this college, Dr. A. Vijayan, for his efforts to enable this seminar to be held at the national level. I welcome you, sir. I wholeheartedly welcome our Vice Principal, Bursar, and IQAC Coordinator for providing all the facilities for the smooth conduct of this webinar. I welcome you, sirs. I happily welcome all the faculty members and students from various colleges for sparing their valuable time and joining with us online. I would like to welcome all the faculty members of our department who always have been proactive, hardworking, and dedicated to make every event a great success. Finally, I happily welcome our students for taking their time out and be here online. Thank you all. Thank you.
Thank you, madam, for your welcome address. Now let me invite the principal of our college, Dr. K. Paul Raj, to give the presidential address.
Yes. Thank you, sir. It's audible.
Yes, sir. You're audible, sir.
Thank you, sir. Right. Most beloved and honorable correspondent cum secretary of our college, L. Rajadure, resource persons of this today's webinar. One of my first friend, Dr. J. John, son of Soil, who is working as an associate professor and head of the Department of Mathematics, Govt College of Engineering, Tirunelveli, and another resource person, Dr. J. Basker Babujee, associate professor of Mathematics, Anna University, Chennai, and the IQAC coordinator, Professor Kibi Thomas, the organizing secretary, Dr. A. Vijayan, the head of the Research Center of Mathematics of our college, head of the Department of Mathematics, Dr. Pramila Inbaros, faculty members who are associated with this webinar for smooth conduction of this program, and participants as a faculty members, our research scholars, our students from various states of our country. On behalf of the NMCC family, I welcome you all. Actually, during this lockdown period, we are enabled to continue our teaching learning process mainly through online mode. Our college, mainly IQAC, and many departments as well as committees have been conducting various online programs such as webinars, workshops, faculty development programs, quiz, etc. for the benefit of our students, research scholars, and faculty members. So today's program, webinar organized by the Department of Mathematics, is one of the kind of program, online program, entitled on few graph concepts and their chemical applications. Since I belong to the botany department, I know the taxonomy, the topic taxonomy is a traditional subject, but nowadays new emerging fields are there, such as biotechnology, genetic engineering, etc. Similarly, in mathematics, the graph theory is a fast developing research area in mathematics. It has many applications in the field like networking, chemical, computer related problems, etc. In this webinar, the main focus is on Vertex Steiner number of graphs and the chemical graphs. Vertex Steiner number is a new concept introduced just recently. I heard that active research is going on in this area, which is highly applicable to medical as well as biological field, especially anti-HIV activity as well as anti-cancer activity. I hope the two resource persons are highly expert in this particular field. By their presentations, all the participants can be enriched and enlightened with a new idea, the noble idea, which can be used for their research activities. So by these few words, I conclude my presidential address. In the meantime, I congratulate the Department of Mathematics and Research Center, mainly the head of the Department of Mathematics, Dr. Pramila Inparos, the Research Center head, Dr. A. Vijayan, and all the faculty members associated with for conducting this program, and also our IQAC coordinator for cooperating for conducting such a academic programs, academic online programs in this campus. I also thank our honorable correspondent for his kind motivation, support, cooperation for all academic and non-academic activities in this campus. I wish all the best. Thank you.
Thank you so much, dear Principal, Dr. K. Palraj, for the presidential address and the nice words that you have spoken. Now, actually, as per the schedule, we have the felicitation by Advocate L. Rajadurai, our correspondent, but he has got some technical issues. He is not able to join right now. We'll wait whether he could join later. So now we go ahead with the first session of today's national webinar by Dr. J. John. So before that, let me invite Dr. G.D. Suresh, Assistant Professor of the Department of Mathematics, to introduce the resource person, Dr. J. John.
Good afternoon, everyone. It is my pleasure to introduce the resource person for the first session of today's webinar, Dr. J. John, Associate Professor of Mathematics, Government Engineering College, Tirunelveli. He did his UG in St. Xavier's College, Palankotai, PG in Scott Christian College, Nagarkoil, MPhil in MK University, and PhD in MS University. He has 25 years of teaching experience. He has published around 75 research articles in national and international journals. He has 25 years of research experience. Under his guidance, 8 candidates were awarded PhD degree, 4 have submitted their thesis, and 6 are doing research work. He has presented papers in 13 seminars and conferences. He has conducted 2 seminars. Now he is going to give a talk on Vertex Steiner number of a graph. Once again, I welcome Dr. J. John for this webinar.
So many scholars are doing research in this graph theory, especially in South India. 90% of the scholars are doing research in graph theory. Now, in graph theory, there are so many concepts: domination, labeling, coloring, distance in graphs. In distance in graphs, there are so many types. One is geodesic. Another one is detour. Geodesic means shortest path. Detour means the longest path. Monophonic means chordless path. And extension of geodesic is Steiner distance. Now today I give a talk in Steiner concept in graph. First I give introduction in Steiner concept. After that I go to Vertex Steiner number of a graph. Now see, I think all of know what is a graph. A graph contains a pair V, E, where V is non-empty set whose elements are called vertices of G. E is set of 2 elements of set of V whose elements are edges. The sets V and E are the vertex set and edge set respectively. Now the order, number of elements in V is denoted by P, and the number of elements in edge set is denoted by Q. If P equal to 1, then we say G is a trivial graph, that is only one vertex, there is no edge. Now geodesic. Geodesic means shortest path, that is for vertices U and V in a connected graph G, the distance du, V is the length of a shortest UV path in G. Length of a shortest UV path in G. A UV path of length d of u, V is called a UV geodesic. Sometimes shortest path, sometimes longest path. If your longest path is called UV. Sometimes longest path is very useful. Shortest path means in bus service or communication links, shortest path are very useful. Longest path means in EB connection, we cover all the straits. Water connection, we cover all the straits. In that situation, longest path is very useful. Now here we consider shortest path. Now see here, consider this graph. in this graph, consider the V1, V3 paths. There are 4 paths. They are listed in the right side. V1, V2, V3 is one path. V1 right, that is right side. Another one is in left side. V1, V5, V4, V3. Another one is V1, V2, next left. V5, V4, V3. Another one is V1, V5, next V2, V3. There are 4 paths. In this, the shortest path is the first path. That is, number of edges in the path is 2. V1, V2, V2, V3. Therefore, distance between V1 and V3 is here 2. Here, the longest path is V3. V1, V5, V1, V2, V5, V4, V3. Here, number of edges is 4. Therefore, the detour distance is here 4. Here, geodesic shortest distance or distance is 2. Now, I go to Steiner distance. That is generalization of Steiner distance. For taking Steiner ordinary distance, we need 2 points. That is 2 vertices. Now here, in Steiner distance, we want a structure. Structure means a set. We need a set, 2 or more. If the set contains 2 vertices, then Steiner distance is same as ordinary distance. Now, if the set contains more than 3 vertices, how will you find the distance? That is the question. For that, the Steiner distance is the number of edges in a minimum tree containing every vertices of W. W எல்லா verticesம் என்ன அப்படிப்பட்ட ஒரு மினிமம் ஸ்டெய்னர் ஒரு ட்ரீ எடுக்கணும். அந்த ட்ரீல எத்தனை எட்ஜஸ் இருக்கோ அதுதான் ஸ்டெய்னர் டிஸ்டன்ஸ். அப்ப அந்த ட்ரீ வந்து ட்ரீ வித் ஸ்டெய்னர் டிஸ்டன்ஸ் D of W is called Steiner tree with respect to W or a Steiner W tree. We call this as Steiner W tree. W tree means that tree and minimum tree, that is very important, minimum tree that contains every vertex of W. Now W must be subset of V of G. Now see, if you take shortest path previously, I take this V2, V4 vertex. There are 2 geodesics. One is V2, V3, V4. Another one is V2, V5, V4. Similarly, there are 2 geodesics, but in V1, V3, there is only 1 geodesic. Similarly, here also, in Steiner W tree, there may be 1 Steiner W tree or more than 1 Steiner W tree, but the length is same. Length must be all the trees having same length. எல்லாத்துக்கும் ஒரே length இருக்கணும். I see one example. I take this graph. This graph I have taken V1, V7, V6. Now there are 3 elements. Therefore, it is a set. Set contains 3 elements. If it contains 2 elements, all the distance and Steiner distance are same. Now you find a tree which connects every vertex of W. I take W equal to V1, V6, V7. I take the extreme end vertices V1, V6, V7. You find a tree which connects all the vertices of W such that the length must be smaller, minimum. Now see, there are 3 Steiner W trees containing the vertices V1, V6, V7, containing the vertices V1, V6, V7. Now see, there are 3 Steiner W trees. All the trees having same length. Length is number of edges 4. Therefore, Steiner distance is here 4. Steiner distance is 4. Here 3 Steiner W trees. T1, T2, T3. Sometimes there may only 1 Steiner W tree. Right? Now, very important note: the tree end vertices of trees are always elements of W. That is very important. End vertices of tree are elements of W. Otherwise, we can minimize the length. Another one, the converse need not be true. See the third T3, there are two end vertices, but there B1, B7, they are elements of W, but B6 is not an end vertex of T3, it is inside. End vertex of T3 must be element of W, converse need not be true. Now see, next, already I have told, if W contains two elements, then UV geodesic is same as steinar W tree. If induced W is connected, I think you know what is induced W. That is, if you induced the graph W, you get a subgraph, it must be connected. If it is connected, then D of W is mod W minus 1. That is a result in steinar distance. D of W equal to mod W minus 1. Now I go to steinar number and I next to go to vertex steinar number. I explain what is steinar number of a graph. Let G be a connected graph with at least two vertices and W subset of B of G. Let S of W denotes all vertices belongs to steinar W tree. S of W nu solradhu steinar W tree la ulla ella vertexayum collect pannunga. If S of W equal to B, whole vertex set, then WA is called a steinar set. The steinar number S of G is the minimum cardinality of its steinar sets, and any steinar set of cardinality S of G is a minimum steinar set of G. Now see, if G of W is connected, then you get a spanning tree of W. It contains element of W only. S of W equal to W. If G of W is connected, then S of W is W. Now see here, again I taken the same example first because we have familiar with the example already. I explained this. I have taken the same vertex set W equal to B1, B6, B7. Now here, three steinar W trees are listed. Now, what is S of W? S of W is the vertices lying in the steinar W trees. That is, S of W equal to B of T1 union B of T2 union B of T3. That is, you collect all the vertices lying in the steinar W trees T1, T2, T3. Now you take the union, you get the whole set. See, the set contains 7 vertices. Here B1, B2, B3, B4, B5, B6, B7. Here S of W is B. Therefore W is a steinar set. Now therefore W is a steinar set. Therefore steinar number is less than or equal to 3. Now how we prove it is equal to 3? Now there is no two element set is a steinar set of that G. There is no two element set which is a steinar set. Therefore S of G is not equal to 2. Therefore S of G equal to 3 means that W contains 3 elements. W contains 3 elements. B1, B6, B7. That is the cardinality. But steinar distance 4. Steinar number is 3 for this graph. Right? Now I take another one example. Here in this example, B3, B6, B7 I have taken. B3, B6 I have taken. There are 3 steinar trees. We can write so many steinar trees. I have taken 3, T1, T2, T3, that minimum steinar trees containing elements of W. Here, same as the previous, B of T1 union B of T2 union B of T3, right? Therefore, we get the set. Therefore, here also we check there is no two elements of the steinar set. Now the vertex set, the W contains B3, B6, B7, 3 elements. Therefore, steinar number is 3. Now here extreme vertex plays an important part. There are so many definitions for extreme. You know, extreme means either maxima, minima, like that, top or bottom. Never it is lies inside a geodesic, not an internal vertex of a geodesic. It must be, it is starting or ending of a geodesic extreme vertex. Now see, extreme vertex means B is said to be extreme vertex. One definition is collect neighborhood of B, the induced set will be a complete graph. That is one definition. Otherwise, you take any adjacent vertices of B, X here, X and Y, say X and Y, then XY must be an edge of E of G. That is the definition. That is, it is nothing but complete. For complete graph, any two vertices, there must be an edge. Here, any neighborhood must be connected by an edge. That is the definition. Here, B1, if you consider B1, its neighborhood are B2 and B5, they are connected by an edge. Therefore, B1 is a extreme vertex of this graph, but B2 is not an extreme vertex because its neighbors are B3, B5, B1. Now, B1, B5 is connected by an edge. B3, B1 is not connected by an edge. Therefore, B2 is not an extreme vertex. B3 is not an extreme vertex. Similarly, others, there is only one unique extreme vertex. It is B1. Now, each end vertex is an extreme vertex. Converse need not be true because we have seen only extreme vertex B1, which is not end vertex. Now, see, we have seen you have, I think you have studied coloring, domination, geodetic, and so on. So many. See, if W is a dominating set or geodetic set, W union X is also a geodetic set or dominating set where it's not a W. Now, that is called super hereditary property. If one set obeys a property, then union of any numbers, any elements obeys that property. That is called super hereditary. But Steiner set does not obey super hereditary property. For example, consider the cycle C4. Here B1, B3 is a Steiner set. B1, B3, one Steiner tree is B1, B2, B3. Another Steiner tree is B1, B4, B3. Now this is a Steiner set. Now see, B of B1 union B2 equal to B. W is a Steiner set. Steiner number is 2. W contains 2 elements. Now I take W union B2. W is B1, B3. W union B2 is W1, W2, W3. Therefore, see, that is which is connected in the graph. Here, W1 is connected. W1, G of W1 is connected. Therefore, you get the spanning tree of W1. That is W1, W2, W3 is the only Steiner W1 tree for W1. Here, S of W1 equal to V of T, V1, V2, V3 not equal to V. W1 is not a Steiner set. But V1, V3, W is a Steiner set. W union V2 is not a Steiner set. That is why here all the researchers are struggling in Steiner set. Some only few researchers are doing doing research in the Steiner area, Steiner concept area. All right. Now I go to the main topic. Before that, application. Now Steiner tree have application to multi-process computer network. See, computer network, there are so many processes are connected. Now communication is linked by wire or anything. Now suppose the primary requirement that communication a message from a processor X to a collection W of other processors to minimize the communication links that are used. Then a Steiner tree for W union X is then optimal way of connecting these vertices, right? W union X Steiner tree தான் அந்த X-க்கு connect பண்ற எல்லாத்துக்கும் minimum link வர set, right? Right? Now see, here this is our motivation because in graph theory, searching computer, there is searching the data, searching anything. There binary search. There are so many searches that in binary search they use tree. If the searching in computer is tree, therefore W union X is the minimal search for connecting all the vertices. This motivated us me to define a new concept, Steiner number of a vertex, Steiner number of a graph. Now, vertex Steiner number of a graph. For each vertex in a graph, we can find a Steiner set. Previously, we can find a Steiner set for whole graph. Here, for each vertex, for each processor, we want a W to minimize the communication link. That is the concept. Therefore, for each computer, we need a communication link to other computer such that we connect all the computers very shortly. That is called vertex Steiner. I take X a vertex, W a proper subset such that X not belongs to W. That is very important. X not belongs to W. Then W is called an X Steiner set of G. If W union X is a Steiner set of G. W union X is a Steiner set. That is, W union X is the optimal way of connecting all the computers. That is the application of Steiner W tree. Therefore, this motivated me to define the new concept, vertex Steiner number of vertex Steiner set or X Steiner set if W union X is a Steiner set. Now remaining is as usual. The minimum cardinality is vertex Steiner number. It is denoted, the minimum cardinality is denoted by Sx set. Now hereafter W union X tree, it is tedious. Therefore I write W X tree instead of Steiner W union X tree. I write Steiner W X tree. Now this definition can be written in another way. We defined Steiner set by the same way. I now define the vertex Steiner once again. Now see, let X be a vertex of a connected graph G and W subset of V of G such that X not belongs to W. Let Sx of W denote the set of all vertices belongs to a Steiner tree. Here S of W denotes set of all vertices belongs to Steiner W tree. Here W X tree means W union X tree. If Sx of W equal to V, then W is called an X Steiner set of G. Now see, I take this example. For each vertex, we can find a Steiner set. Now, for each vertex, there may be one Steiner set, minimum Sx set means minimum Steiner set, or more than one Steiner set as in domination. The cardinality is here: first one 2, second one 3, fourth one 4. Now I explain with an example. For the set, for the vertex X equal to V1, X equal to V1, I take V5 because V5 is an extreme vertex. It does not comes on internal but belongs to internal vertex of a geodesic. Therefore, we take that vertex V5. I take V5 and V6. What is the Steiner minimum Steiner set of W1? Right? That is the question. Now, for that V1. What is the minimum Steiner set of V1? I take W equal to V5 Vx. Now we find W union X set. W union X means X is V1 here. I take W union X. W union X means V1, V5, V6. Now you find Steiner W tree for V1, V5, V6, or Steiner tree for W union V1. W union V1 is nothing but V1, V5, Vx, that is Wx. We find W Steiner Wx tree, that is minimum tree containing V1, V5, V6. There are two trees. Now find Sx of W, V of T1 union V of T2. You take the union, you get V. Therefore, W equal to V5, V6 is a Steiner set for the vertex V1. here the number is 2 because there are 2 elements in W. Therefore, the vertex Steiner number for that vertex is 2. Similarly, I take another one vertex. I have take only one vertex. Now, if you take B2, you get B1, B5, B7. Another one is B1, B5, B6. Another one. Similarly, for B3, there is only unique B1, B5, B6, B7. Answer is 4. Similarly, for B4, you check. I send that PDF. You check all the for all the vertices. It is 2, 3, and 4. But if you check for this tree, Steiner number is 3. For this tree, for this graph, Steiner number is 3. Vertex Steiner number is 2, 3, 4. 2, 3, and 4. Now see. Now you know extreme vertex. For proof is not given. Every extreme vertex of G, other than the vertex X, belongs to every Steiner set of X Steiner set of G. Each extreme vertex, whether X is extreme or not, because if it is extreme, we does not take that vertex in W, because X not belongs to W. If other extreme vertices must be taken. Now, no cut vertex belongs to minimum X Steiner set of G. That is the last one. Similarly, other theorems are there. For time simplicity, I simplify this. I take last one. No cut vertex of a connector graph G belongs to any minimum X Steiner set of G. Now see, theorem for the complete graph, Sx of Kp equal to P minus 1. P is number of vertices for every X in G. Now because for the complete graph, every vertex is an extreme vertex. We take a vertex X, for a vertex X, we take the remaining P minus 1 vertices, then only it is a vertex Steiner set. Therefore, answer is P minus 1. For a tree, if X is a cut vertex, that is internal vertex, then Sx of T is number of end vertices. Otherwise, for an end vertex, because tree contains only cut vertex and end vertex. Now, if X is an end vertex, then it is K minus 1. That is number of end vertices minus 1. Now, for the cycle, CP, 1 if P is even, 2 if P is odd for every X in P of CP. For complete bipartite graph with the bipartite sets U and V, it is M minus 1 if X belongs to U and N minus 1 if X belongs to V. For the wheel graph, it contains one full degree vertex K1. Vertex of K1 is full degree. Therefore, it is P minus 1. For that full degree, it is P minus 1. For the remaining vertices, it is P minus 4. Now, the vertex Steiner number has a lower bound. For any vertex X, the lower bound is 1 and upper bound is P minus 1. Ss of G lies between 1 and P minus 1. Now, when the lower bound is sharp, let G be a connected graph of order P greater than or equal to, then for a vertex X in G, Xx of G equal to 1 if and only if there exists a vertex Y such that every vertex of G is on a dimensional path joining X and Y. X and Y antipodal irukkanum. X and Y antipodal na D of X Y comma Y diameter irukkanum. Appadi irunduchuna Xs of X G vandu 1. Example, for a cube ku vandu Xs of G equal to 1 for every vertex X in Qn. Now, one theorem, Sx of G less than P minus 1 if and only if induced W union X is disconnected. P minus 1 irukum ana P1 minus 1 க்கு கம்மியா இருக்கணும்னா induced graph of W union X வந்து disconnected ஆ இருக்கணும். That is necessary and sufficient condition. Using this is the upper bound for geodetic vertex stainer number x's of g equal to p minus 1 if and only if degree of x equal to p minus 1. Degree of x equal to p minus 1. Because if degree of x is p minus 1, then it is linked with every other vertices. Therefore, we take all the vertices. Then only it is a stainer set. Therefore, it is p minus 1. If x is a full degree vertex. Similarly, if xx of g equal to p minus 1, by previous theorem, we can prove if it is less than p minus 1, we get a contradiction by using the previous theorem. Therefore, dx of equal to p minus 1. That is the upper and lower bounds for this. Now, comparison of stainer number and vertex stainer number. Now, which is greater? Question: stainer number greater or vertex stainer number greater? That is the question. Now, see, if B is a cut vertex of a connected graph, W and X stainer set of G, then W belongs to every stainer WX tree of G. That is, this is actually a theorem. I give you an observation here. Now, if B is a cut vertex, that cut vertex belongs to every stainer WX tree. Similarly, no cut vertex of a connected graph belongs to any minimum stainer set. Using these two concepts, I state a theorem. Let X be a cut vertex of G, then W is a vertex stainer, minimum vertex stainer set, that is SX set, if and only if W is a S set. If X is a cut vertex, then vertex stainer set and stainer, minimum stainer set are same. X cut vertex irunda mattum. Now see, now we have theorem. X is a cut vertex of G, SX of G equal to S of X. Cut vertex irunda random number equal. And the X cut vertex irunda whole set to the stainer set number and the cut vertex to the stainer number same. Ana converse vandu true irukadu. Converse may not be true. Now consider this graph. This graph, see for this graph, V1, V4, V2, V3, V6 are the only two stainer sets of G. Therefore, S of G vandu 2. Also, the vertex for the vertex X equal to V5, V2, V7 and V4, V3, V1, V3 are the only two SX sets of G. SX X1 2 தான், stainer number 2 தான். ஆனா X வந்து cut vertex கிடையாது. இங்க V5, X வந்து V5 அந்த கிராஃப்ல cut vertex கிடையாது. அத கான்வெர்ஸ் கிடையாது. Which is greater? Now stainer number is less than or equal to SX of G plus 1. Because you take X a vertex, W and X stainer set, then W union X is a stainer set. That is the definition. Therefore, is less than not W union X, because stainer set is minimum. Stainer number is minimum. X of G is less than or equal to mod W union X. Therefore, W is a minimum XX set. Its cardinality is SX of G. X has cardinality 1 plus 1. Therefore, S of G less than or equal to XX of G plus 1. Now, when this inequality is equal, that is the theorem for any vertex X in G, S of G equal to X of G plus 1, if X belongs to a minimum stainer set of G. If X belongs to a minimum stainer set, then S of G equal to XX of G plus 1. Now, observation, the second observation is proved in stainer number of a graph. For the complete bipartite graph, stainer number is minimum of m comma n. Here minimum is now for stainer, we have seen just now sub m comma n equal to m minus 1 belongs to b. Now, all graph theory asks question, if they define a new parameter, then find a relation between existing parameter and a new parameter, and ask a question for any two positive integers a and b with the here s of g is lesser, s of g less than or equal to b. Thus, there is a connected graph with existing parameter a, number a, and new parameter number b. That is the question, right? For this, I have drawn a graph with I think 20 or 25 vertices. When the referee in the review process, the reviewer comment, it is a big graph. You can take the complete bipartite graph. It is very simple. This construction is done by the reviewer of this paper. He is constructed in the comment. See, if we take the complete bipartite graph, if a equal to b, we take the tree. For tree, if you take a internal vertex x, sx of g equal to number of end vertices, it is a. S of g is also number of end vertices, is a. For 2 less than or equal to a less than b, you take the reviewer told you take g equal to k a b plus 1. For g equal to k b plus 1, now b is greater. Therefore, Steiner number is b plus 1. Therefore, Steiner number is a. And you take a vertex from W. And now see the previous observation. Sx of kmn equal to n minus 1 if x belongs to B. Now you take a vertex from W. Sx of W equal to n minus 1. It is B plus 1 minus 1. B plus 1 minus 1 is B. This is the simple graph. Why you go to construct a graph with so many edges and so many vertices? The reviewer comment. Therefore, according to this comment, I modified the theorem. Right? That is the end of this. I worked here. This Steiner minimum vertex Steiner set is not unique. Therefore, we can find upper Steiner number, forcing Steiner number. Similarly, we can connect this parameter with the monophonic, geodesic, and so on. There are so many open research in this area. The budding researchers, you can work in Steiner number. If you have any doubt, you can ask me. Now see references. These are the references. Actually, Steiner number is introduced by Chatran and P. Chang in 2002. They proved every Steiner set is geodetic set, but after that, Pelayo disproved it is not so. Every Steiner set need not be a geodesic set. Next, another one proved every graph having diameter 2, in which every Steiner set is a geodesic set. Later, I disproved that in a journal, that is 8, that is command on analogs between geodetic number and Steiner number filament. It is a Stein citation index journal of impact factor 0.8, I think. This journal, I disproved that. In this journal, they proved every graph having diameter 2 geodetic set is Steiner set. But I disproved the result with the counter example. It will appear accepted for publication. It will appear in this year. Now another one is after that, in which type of graphs Steiner set is geodetic, I discussed and I submit in Internet Journal of Computer Mathematics System Theory. It is also accepted. Now in this series, I think, like to me, I published so many papers in reputed or Science Citation Index journal. First one is upper restraint Steiner. It is discrete mathematics algorithms and application. Total Steiner number, only single other. Vertex Steiner number, that is in translation on combinatorics. You go to the website, you download every composition and so on. Edge-Steiner self-decomposition, that is decomposition with the edge geodetic set, and coloring with the geodetic set. Another one is open detour number of a graph. Open detour number of a graph, that is a detour concept. Edge geodetic self-decomposition, that is RIRO operation research. It is in aims of scopes of this journal. Graph theory papers are accepted. This is a SCI journal, SCI, Science Index journal. That paper is also accepted for publication. It is article is published. The DOE number is given. Right. With these words, I finished my topic. Now see, it is a privilege for me to present my research in the webinar. I thank the correspondent, the beloved principal, HOD of Mathematics, faculties, Department of Mathematics, the IQAC coordinator to conduct the Zoom meeting, to conducting this webinar in a successful manner. I thank beloved Dr. A. Vijay sir for giving the opportunity as a resource person in the webinar. Thank you, one and all. Thank you, sir. With these words, I finish. Sir?
Thank you, sir. Thank you. Now we have the questions, if there are any. I have asked the participants to either send questions to your chat or to the chat of Dr. Vijay. So I think they can compile the questions, and they are also given provision to raise their hand. They'll be given option to ask questions. So now there is one hand raise from Mr. Gio Solomon. So I'm asking him to unmute and ask the question.
Hello, sir.
Hello, madam.
Hello, sir. One doubt. Is the Steiner graph or any application in chemical graph theory?
No, yes. Steiner distance is applied in chemical graph theory, but that Steiner chemical graph theory is done by I think give lecture by that resource person Basker Babujee sir, right? This also have so many chemical applications. MAO, Yapin Ma on China author. He survey an article Steiner distance in graph, that is in that is search the net Steiner distance in graph a survey. It is done by MAO. He has given so many applications in chemical theory. Actually, chemical graph theory is lecture is given by Basker Babujee, right? Now have tremendous work in that area, chemical graph theory with Steiner distance. You see the journal chemical graph theory journal of chemical graph theory. See journal and site search the applications of Steiner distance in chemical graph theory. Right? My
okay, sir.
Steiner said that is PU concept in graph. That is only for me. The remaining is for to Basker Babujee. Okay.
Okay, sir. Thank you.
Let me invite Dr. Lal Gibson to introduce the second resource person, Dr. Basker Babujee.
Good afternoon, one and all. It is my privilege to introduce our second resource person, Dr. J. Basker Babujee, Associate Professor of Mathematics, Anna University, Chennai. He did both MSc and MPhil from Madras Christian College, Chennai, and PhD in Graph Theory from Jawaharlal Nehru Technological University, Hyderabad. He has 210 publications in academic journals and international conference proceedings. He has around 27 years of teaching experience. Currently, he has an associate professor in the division of Applied Science and Humanities in Anna University, Chennai. He has guided 11 PhD scholars and 31 MPhil candidates. His research area is dot theory, formal languages and automata theory, number theory and cryptography, and geometric functioning theory. Now, he is going to deliver chemical graph theory and its application. All structural formulas of chemical compounds are molecular graphs where vertices represent the set of atoms and edges represent the chemical bonds. In this presentation, some topological indices of chemical graphs are taken for analysis and also the correlation between VNR index, Estrada index, etc. Finally, few topological indices are taken for the development of model for prediction of anti-HIV and anti-cancer activity of some marine alkaloid compounds. Such eminent personalities with us. On behalf of our participants, once again, I welcome you, sir. Sir, welcome.
So thank you, Dr. Lal Gibson,
Thank you.
the Assistant Professor of the Department of Mathematics, for the nice introduction. And now the floor is yours, Dr. J. Basker Babujee, sir.
Hello. Can you hear me, sir? Hello.
Yes, yes, you are audible, sir. Yes, you are audible.
Good afternoon, one and all. Is it audible, sir? Is the PPT okay? Hello.
Yeah, PPT is visible. You are audible. Yes, yes.
Yeah, thank you. So let me congratulate the Department of Mathematics of Nesamony Memorial Christian College for conducting this beautiful webinar program in this pandemic period. I personally thank the head of the department, Professor Vijay, sir, Professor of NMC College, and the entire department. Okay. The topic, chemical graph theory, and today. So let me go from the basic very quickly and then tell some organic part chemistry and then enter into my concepts. So we know the history of graph theory. I need not spend more time. The father of graph theory, Euler, 1736, when he came out with that Eulerian trial and then said that if you require a solution, then certain conditions are required for an Eulerian graph. So the Königsberg bridge problem. So this is the Königsberg, where you have the 4 land areas and 7 bridges, and the river passing with 7 bridges, and that was interpreted as a graph by this great mathematician Euler, and later the subject started growing. So all these basics I hope that people will be knowing. So if the degree is even, all the vertices have even degree, then we can think of the Eulerian a circuit. So that was the start of the subject and so on. Now, basic definitions of graph theory. I hope all are well versed with the basic definitions of graph theory. So let me just scroll all these slides, preliminary slides. A graph is a 2-component with the vertices and edges, and so on. So this is a simple graph which have the degree of the vertex A is 3, 2, and B is 2, and C is 3, and this is called pendant vertex D. The vertices of the degree of the vertex is 1. It's called pendant vertex. Right. So this is a complete graph. Yes, this is a complete graph with 4 vertices. It's also called regular graph. Okay, so complete graph means all of us know that any 2 vertices can be connected directly by a path. sorry, directly by an edge. If it is connected directly by a path, it is a connected graph. If it is connected directly by an edge, it is a complete graph. And almost here it's a K4 symbol. And this is there is no edges graph. So likewise, more and more basic concepts are there. I will skip all these concepts. Let's go directly to this is complete bipartite graph. If you give directions called digraph, then the most important thing is the trees, where it is has no cycles, connected acyclic graph, and more number of trees is said to be forest, and so on. Rooted tree, internal vertices, root vertex, and all those things. Fine. So the idea is today to introduce already the formal speaker has given some introduction to your chemical graph theory, topological process. Let me not waste my time, our time, so precious it is. Topological indices is essentially a numerical molecular descriptor associated with the molecular structure. In order to make it easier for our readers and understand the method coding chemical structures from molecular graphs, we can really enjoy the concepts like adjacency matrix, characteristic polynomial, Laplacian matrix, topological indices like linear indices, Rho index, Zagreb index, which will be discussed. So that is what the importance of algebraic concepts in chemical graph theory are highlighted to motivate the researchers in this area. So that is the real work to motivate the researchers. Fine. You know that graph theory has wide applications in engineering, physics, social, biological sciences, linguistics, and numerous other areas. So any physical situation involving discrete objects with some relationship can be represented as a graph. So if you have a set of points, if you try to relate them, then you can draw a graph. Then as we mentioned earlier, the basic idea is the degree of the vertex. How many edges are incident on the vertex is counted, that's called degree. So the minimum degree is small delta, rotation, maximum degree is capital. Quantitative structure activity relationship, the most in physical chemistry. So this is the study where we can have an interplay between graph theory, that is especially chemical graph theory, to the compounds. Right. So let us start with the carbon. Carbon is found in many different compounds. It is used in food, clothes, cosmetics, gasoline, fuels, etc. Most abundant element in this. Carbon is a very special element because it plays a dominant role in chemistry of life. So this is the structure. Carbon atom has 6 electrons, out of which 4 electrons are the outer cell. It's called the valence. So it requires to be saturated. Carbon valence is 4. Hydrocarbons. What is hydrocarbon? The compound which has only hydrogen and carbon is hydrocarbon. So when you think of hydrocarbons, there are two types of things. One is saturated, another one is unsaturated. Saturated means you should balance. The valence should be balanced. Valence is 4. Look at this here saturated compound. There are 2 carbon atoms and 6 hydrogen atoms around it. So here hydrogen, 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 and that is 3. And here also hydrogen, hydrogen, hydrogen 3. So one more is balanced with these 2. So there's a share between these 2 carbon atoms. So totally the 4 outer electrons are balanced here. So sharing has been done with this hydrogen, 3 hydrogen and 1 carbon. So this is called saturation. Look at this right side. It is unsaturated. Unsaturated means still you have to balance it. So the 4 is not satisfied because 2 hydrogens are missing. Because of that, there is just one double bond is created. This is called unsaturated. Suppose if I remove these 2 hydrogens also, one more bond will come. So triple bond, maximum 4 valency. So triple bond and 1. So whatever may be double bond or triple bond, it is unsaturated. Okay, here it is saturated. So we are interested here. What about saturated or unsaturated? We are going to look this as a graph later stage. That is alkanes. General formula is CnH2n plus 2. General formula. Saturated hydrocarbons called alkanes. So methane, ethane, propane, butane, all these ANA, last 3 ANA, alkane, this methane, ethane, propane, butane, then hexane, and so on. So CnH2n plus 2. So I remove 2 hydrogen, so it becomes a general formula CnH2n minus 2n plus 2 becomes 2n. Because of that, you get a double bond. So all alkenes, ene families, that is methane, ethane, propane, propane, and so on. All these things is you would have studied in our +1, +2 itself in organic chemistry part. Then the last one is you can see that alkynes, that is CnH2n minus 2. We started with the H2n plus 2, removed 2 hydrogen, double bond has come. Again, remove 2 hydrogen, triple bond has come. So this is a CC triple bond. So this YNE, alkynes, methyl, ethyl, propyne, butane, and so on. So all these things these three are the basic things. Now, for us, we want only bond between compound 2 carbon atoms, whether it is alkane or alkene or alkane. For a mathematician, the bonds are required. A single bond, a double bond, a double bond. Okay, so what is the next step? We want to correlate some physical properties, predict physical properties, that is like physical, chemical, biological properties from the molecular structure. That is the most important unsolved problem in critical and chemistry, environmental chemistry, and science as well as. So it's necessary for us to understand the structure of a chemical compound. Most important is we should be structure, how it is designed. Once you have the structure of the compound, then we can represent an object giving information about numbers composing this connectivity. That is called topological. So a topological representation of a molecule is called a molecular graph. So let us see here. Look at this 3 carbon atoms, C3, substitute N is equal to 3. Okay, so CnH2n plus 2. So it's 6 plus 2, 8. So 8 hydrogen atoms. So this is a propane molecule. Propane molecule. So what is just and lines for the edges. Here all single bond, no problem. It's very clear. But as I mentioned earlier, single bond or double bond for us, we put a line. Whenever you have a bond, saturated or unsaturated, we put line. So this representation is called molecular graph. So all the atoms are represented as vertices, and all the bonds are represented as edges. But again, to refine this, you remove all the hydrogen atoms. You think only the carbon-carbon skeleton. Okay, remove all the hydrogen atoms, take only the carbon. So this is called hydrogen diplicit graph. So that is what we require for our study, the carbon-carbon skeleton. The molecular graph is a collection of points representing the atoms in a molecule, set of lines representing components. So this is our molecular graph, hydrogen diplicit molecule. It's a methane molecule. Center is a carbon, 4 hydrogens are there. So methane molecule. So if you want to represent the methane, it's only a dot, single vertex. Okay. So that's with balance. So let us now think of the next idea. Once we have a structure, what we are going to do with the structure? So take a molecular compound, project structure, input as a graph. So the construction and investigation of topological indices. So what is a topological index? It is a number. Index means number. We can also say number. So which is being calculated from the graph. Topology here in the sense that it's a structure with the points and lines. So in engineering also we say topology, star topology, circuit topology, path topology. So any network with dots and lines we say topological network. So for a graph, we want to find a number. Each graph we want to find a number. How to find a number? There are 2 ways to find numbers that we'll be telling later stage, either by distance or by degree. Degree means degree of the vertices. So here the varieties of problem in pure and applied graph theory can be treated and solved efficiently in polynomials. See, always you see polynomials play a major role. Even in our pure subject, whenever you think of a function, say analytic function, okay, can you have a series here? Okay, you have Taylor series, Lorentz series. You take a Fourier series. Whenever you have an expansion for the function in terms of series, okay, the coefficients play a major role. If you take a polynomial of a quadratic or a cubic, we can talk about the roots of the polynomial, zeros of the polynomial. with the help of the coefficients A0, A1, A2, and so on. So polynomial gives us the entire properties of the function. Similarly, can we construct some polynomials? Polynomials provide both a convenient and powerful mathematical tool and valuable proof techniques in the fields of graph theory. Within the past decades, indices have evolved which which depend solely upon the structure of some matrix, like adjacency matrices used to represent the chemical compounds. Look at this compound. This compound is having 1, 2, 3, 4 in straight chain butane. The second place you have 2 methane, CH3, CH3, right? So this the second position we have 2 methane, so 2 dimethyl butane. This is the compound. Right. This compound, what we do is we draw the molecular graph. So we have 1, 2, 3, 4 as straight chain P4, and then the second position 2 carbon atoms. So this is the compound. So what we are going to do now, we take a molecular structure, interpret as a graph called molecular graph. Okay, next stage, what we are going to do is we write the adjacency matrix. What is adjacency matrix? Whenever there is it's a square matrix, row and column are taken as vertices. Whenever you have an edge between 2 vertices, then I put 1. So 1, 0 matrix. Whenever there is no edge between 2 vertices, I put 0. So if you look at the previous slide, here we have the 1, 2, 3, 4, 5, 6 vertices, V1, V2, V3, V4, V5, V6, we name. And then we can write whenever there is an edge between 2 vertices, we put 1. When there is no edge between 2 vertices, put 0. So here, this vertex has 1, 2, 4 emerging edges. So you can see that we have the second vertices has 1, 2, 3, 4 ones are there. Other 2 places 0. So likewise, we fill the entire matrix adjacency matrix. Fine. So I have taken the chemical compound, draw the structure of the chemical compound, interpret as a matrix, write down the adjacency matrix. Fine. Look at this adjacency matrix. At the outset, you can see that the first row sum all the number of ones. Second row 1, 2, 3, 4. So sum is 4. Third row 1, fourth row 1. Then fifth row here V5 1, 2. So 2. So this gives me the sum, gives me degree of the vertices. So degree of V1 is 1. Degree of V2 is 4. Degree of V3, degree of V4 is 1. Degree of V5 is 2. This is the beautiful property for this. And if you look at the principal diagonal of the matrix, 0. Only zeros. Why it is 0? Because there is no self-loops. There is no self-loop between one vertex to another vertex. It's a simple graph, and therefore there is no self-loop. So all the principal diagonals are 0. So the beautiful algebraic concept, that is your characteristic equation. So suppose I take this matrix, square matrix to be capital A, order n, then I can find a non-zero column vector x, such that lambda for a scalar lambda, that is a scalar lambda for the non-zero matrix, column matrix x, ax equal to lambda x. So this gives me lambda is called eigenvalue, and such a non-zero column vector is called eigenvalue. If I bring it to the left side, and then I equal to take the determinant, I get the equation that's called the characteristic equation. Determinant a minus lambda equal to 0. Okay. What is use of this? If I solve this differential equation, I get the roots. That roots are called characteristic roots or eigenroots or eigenvalues. Fine. Once you solve, you get the n values. So we get for the characteristic polynomial, the characteristic roots lambda 1, lambda 2, lambda. So this is the notation here. The characteristic polynomial of degree n, and will present in the form is CH gx is x power n, CG1 x power n minus 1, CG2 second quotient. So this is A1, A2, A3, so on like that. C1, C2, C3, so on. C. So I can write the characteristic polynomial this way. Well, so let us see here the coefficient. This is always 1. This coefficient is always 1. And then here, if you look at this coefficient, okay, CG1, that's an interesting property. Okay, we'll see what is happening next. So let me take a simple graph G before going to the more further details. Look at this particular graph. This is a simple graph with 4 vertices. And for this graph, if you calculate the characteristic polynomial, okay, lambda a minus lambda x. So look at this characteristic polynomial determinant 4 by 4 determinant. Expanding this used to be x power 4 minus 5x square minus 1. So this is the characteristic polynomial. Something is missing here. X cube is missing here. Constant term is missing here. Fine. Now let us check with the properties. The as well famous theory of equations in algebra. We can see that. What is the second? What is the coefficient of x cube? It's 0 here. But what is really the meaning of the coefficient? It's called the sum of the eigenvalues. Or another way we can say the trace of the matrix. If you look at this earlier, the adjacency matrix, for this adjacency matrix, for the principal diagonal is 0. Principal diagonal is 0, that this trace of the matrix is 0. Because trace of the matrix is 0, the coefficient of x cube is missing. First point. Then it is the product of the eigenvalue or determinant of the eigenvalue, determinant of the matrix, product of the eigenvalues, lambda 1, lambda 2, lambda 3, lambda 4, or is equal to determinant of the matrix. The determinant is 0. That's why constant term is missing here. There's no constant term here. That means when do you get determinant 0, product of eigenvalues becomes 0. When do you get product of eigenvalues 0, at least one eigenvalue must be 0. So likewise, we can think of properties. So look at this. Apart from that property, watch this coefficients. C1 is 0, C2 is minus 5, C3 is 2, C3 is minus 4. Look at this here. What happens here for this matrix? C1 is 0, minus C2. Minus C2 is C2 is minus 5. So minus C2 is 5. Minus C2 is 5. That is number of edges. Coefficient is minus C2 is the number of edges. And minus C3 by 2. That is 4 by 2. And C3 by 2. That gives me number of triangles. So this simple property like this for simple graphs, planar graphs. Okay, when you interpret as a characteristic polynomial and expand coefficient these categories. But what I said earlier is that the algebraic property always this coefficient x power n minus 1. The coefficient of x power n minus 1 will always be 0. So this coefficient that is x C1 0. And this is the determinant of the matrix or product of the eigenvalues. This will become 0 means at least one eigenvalue is 0. So that is the property. So let us see, take a bipartite graph. Take the bipartite graph. Here there are 5 vertices. We will put the one column expansion, and then this is the polynomial. Again, you look at this x power is 0 because the trace of the matrix is 0. And here also x square is 0. In this case, x square is 0. Then the product is also 0. So that means what? This one eigenvalue is 0. So fine. There are 5 roots. 5 roots. This is a complete bipartite graph. Not complete, it's a bipartite graph. You not go for complete, simply a bipartite graph. Bipartite graph, the eigenvalues are plus or minus 1, 0, plus or minus 2. So if the roots are number of roots are what do you say even, then the roots occurs in pairs plus. Number of roots are odd, the positive negative that one will be left out, that will be 0. Suppose this one more vertex is there, v6 is there and connected as a bipartite graph, you won't have this 0. What happens is the eigenvalue, pair of eigenvalues, sum of pairs of eigenvalues. Here look at this property, xi plus n plus 1 minus I is 0. So this is a beautiful result here. Graph is bipartite if and only if xi plus xn minus 1 plus I is 0. In this case, it is odd. Okay, if I have a pair 1 minus 1, 2 minus 2, and one more left out. So if it is even, then we may have 3n minus 3 or again 2n minus 2, or we don't know. This for this example is the case. Likewise, you have plenty of algebraic properties. So what we started is we started with the chemical compound, then draw the structure, interpret as a molecular graph and try to have polynomials. Okay, what is use of this finding the eigenvalues? What is used here is it is useful to find the energy of the compound. So this, if you sum up this case, this what sum of the eigenvalue, trace of the matrix 0. That's a problem. That we can find +1 -1 0. Product of the eigenvalue is 0, so that's fine, right? So in case if you take the absolute value, take the absolute value, modulus of -1, modulus of 1, modulus of 2, then you sum, it's non-zero. So for that, we will find sigma, modulus of lambda is the energy of the graph. Again, that is an application. So in that case, let us see two results. I don't want to go purely into this. This is spectral graph theory part. So I want to tell you some topological integers and use some applications today. That's what my talk is going to be. But to give you a flavor of little algebra, I'm just talking these two theories. If GA and GB are isomorphic graphs, then the characteristic polynomial are same. They coincide. Very standard. But look at the converse. The converse is not true. Thus, if GA and GB are two graphs which has equal characteristic polynomial, not necessarily true that they are isomorphic. They need not be isomorphic, but the characteristic polynomial will be same. Okay, if two non-isomorphic graphs, okay, two non-isomorphic graphs have equal polynomial, we say they are isospectral. This will occur. This possibility is there. Okay. So all this depends upon the adjacency. Characteristic polynomial depends on the adjacency. They need not be isomorphic, but still the polynomial becomes same. Of course, the number of vertices should be same. So it's called isospectral, two compounds. So it's a beautiful chemical property here. So look at the chemical graphs, 2,3 dimethyl and 2-methyl 4-ethyl hexane. They are non-isomorphic. Number of things are different. But what happens? The polynomial is same. Polynomial is same. Both have same qualities. Polynomial. They have equal number of vertices. The compound is not different because the position varies. Where the bonds are there. Okay, where the methyl and instead of 2-methyl, and here look at this. Second and third position have methyl, CH3, CH3. Carbon is standing, hydrogen is represented. So this is 2,2-dimethyl heptane. Whereas here you have second position a methyl, and then fourth position you have an ethyl. It is an hexane. Okay. But the number of carbon atom is same in both. But the structure is varying, the compound is varying, it has totally different colors. Accidentally, what happens? The polynomial coincides. The compound are different. So this is the beauty here. The converse. If graph TA and GB are isomorphic, the polynomials will coincide. For this, we have twisted it all. Just twisted the vertices. The polynomial is same. Very simply. Look at here, the number of vertices are same, but this is disconnected, and the continuity is not there. Okay, so it stands alone here. The polynomial is. So graph polynomials are frequently in applications of graph theory. We say main directions of in theoretical chemistry in which graph polynomials have relevance. There are plenty of theory behind this. Untitled molecular orbital theory related to simple electron models concerned with the topology of conjugated molecules. So the characteristic polynomial of molecular graph function in this context is a scalar theory of chromaticity based on topological resonance energy, where it requires the knowledge of zeros of the class theory of automatic. So like this mono or dimer topological index. So fine. So likewise the theory goes. Fine. So the if you take a polynomial of degree n, it has n zeros. So similarly here also we can write the polynomial zeros. Not necessarily realize all the complex numbers. Okay, you collect the eigenvalues. It's called spectrum. Collection of eigenvalues called spectrum of the graph. Spectrum of the graph is some importance in theoretical chemistry because it intimates the relationship between eigenvalues, the molecular graph, and the chemical molecular concept. So let us see the very famous. When you take the eigenvalues, let's say, what is the bound? What is the range of the eigenvalues? The mathematicians always just the lower bound, upper bound, smaller, big. You also having a range. Which range is the value? Prediction or predictions. So it ranges from minus Dmax to plus Dmax. What is the Dmax valence? Okay, the limits of the graph spectrum settlement, maximum valency of vertex Dmax. So the equality is achieved to the right hand side if all the vertices of the graph have same valence. Equality is achieved on the left hand side if all the graph is also bipolar. Again, beautiful properties are there. So there stands the mathematicians of the beauty. When it is equal, the left side, when it is equal, the right side. Non-isomorphic graphs may possess identical characteristic polynomials. That's all I will explain. Right. So now this is what I wanted earlier in the previous slides. What we had is take a compound, draw the molecular graph, can expand, find the eigenvalues. Very, very useful eigenvalues are useful for us to find the energy of the graph, and the bonds are there. This is a spectral graphic part. So coming to the topological indices, there are two types of topological indices. That is, one is based on the distances. So the distances, plenty of indices are there: Wiener, edge, determinant Wiener, Harare, reverse, reciprocal. The list goes. Okay, there are more than about 40 topological indices, distance based. Then another set of topological indices based on connectivity, degree of the vertex relation, degree related. What is the degree of the vertex? What is the degree of the edge? What will be the degree of the edge and plus the degree of the edges around the first neighbors? So plenty of concepts. Yesterday index, Z index, reformed Zagreb. It's post length 40. This is fine. So this is the man behind this study. 1947, Harold Weiner introduced two terminologies, namely path number W, polarity number. Later, this polarity number, path number was called as Weiner number with his name. So topological index is a numerical parameter of a molecule based on the certain features of corresponding molecular graph. Topological index of a graph is the invariant number called calculated from the graph represented as a molecule. Okay. So this person is Harold Weiner, who started the study in 1947. So he used this to predict the boiling point of hydrocarbons. As I mentioned earlier, hydrocarbons by a linear formula which is given by T equal to AW plus BP plus. This T is the boiling point of the alkane. So the study started, experimented, chemical gravity was starting point is this prediction of boiling point. If you take an alkane, saturated hydrocarbon alkane, what is the boiling point of the alkane? Can be predicted by this relationship. Okay, so W is the Weiner index. W is the Weiner index. We will see what is Weiner index. Next, P is the polarity number. So these two are being investigated from the graph structures. These constants A, B, C are constants. So this relationship itself is a great achievement to start with. So once you know this linear relation, plane equation like T, W, P is there, constant A, B, C is there. Okay, then what will be the use of predicting the volume? See, every time we cannot waste our time in the laboratory to find the boiling point, melting point, molar volume. Sometimes prediction is useful for us. This is the boiling point for this compound. This will be the boiling point or the boiling point of the unknown compound which has been yet to be decided whether it's stable or not. Can be done prediction. So depends upon the chemical reaction. I take two molecules. I take M molecules and N molecules of two different compounds. I put the test tube. I try to do some chemical reaction. I make it the third compound, but the third compound may be a lead compound or an unsaturated compound, or the compound will not exist. It will not stand. It will not withstand. It may just disappear, or the reaction may go backward, or it's not a stable compound. You don't, if A and B reacts, you should get a C. If nothing is happening, that's no use of the reaction. Something is happening, it should be stable. If it is not stable, the third compound is not stable, no use of that. It's not cannot be used, and further it can't be that reaction is a waste reaction. If it is stable, then we can study. If it's unstable compound, it will vanish, or it will go to as a liquid or a gas or whatever. So we are, but at the same time, the outcome, how to predict the boiling point of outcome. this is going to be useful for us. That way, it started to work. Okay? So let us see what is the Wiener index of the graph. So one of the most widely known topological descriptor is the Wiener index, named after the chemist. Wiener index of the graph is defined as the sum of half of the distance. So this is the formula: half of sigma over I, sigma over j, d vi, or you can also use this formula: sigma d of vi vj and I less than j. So here half is there, double sigma. It's a repetition. Here there's no repetition, so a single sigma is there. Fine. And immediately the mathematicians, they say, what is the Wiener index of a tree? For a Wiener index of a tree lies between star graph, star graph and path graph. So let us see the example. We'll come back to this. Look at this example. This is a simple graph with 4 vertices. Okay, V1, V2, V3, V4. Okay, and then these distances have been calculated for the graph. Distance between V1 and V2 is 1. Distance between V1 and V3 is 2. Distance here is the shortest distance. That is most important. Distance between V2 and V3 is 1. V2 and V4 is 1, and V4 is 1. So I will apply the formula. Okay, I'll add all the distances. That is sigma d of VA Vj. I don't want to repeat. If I repeat, put double sigma. Put half of it. So I know repetition is there. Simply add 1 plus 2 plus 1 plus 1. The answer is 8. So the Wiener index of this particular graph is 8. Wiener index of this particular graph is 8. So in computational chemistry, to measure topological properties, quantity structure property relationship, base things Wiener index. Well, so let us take a complete graph. What is the complete graph? Already we have seen any two vertices are joined by an edge. So what is the distance between any two vertices? 1 is the distance between any two vertices. So the complete graph, you have a NC2. You have a NC2 edges. So that means distance between any pair of vertices is always 1, 1, 1. So this n square minus n into n. So for the complete graph. And that will be small value because all the vertices are connected by edge. The distance for any two vertices is always 1. The distance is only the neighboring vertex distance is 1. Afterwards, the distance, suppose you take V1 to Vn. V1, V2 is 1. V1, V3 is 2. V1, V4 is 3. V1, V5 is 4. V1, Vn is n minus 1. For a path graph, it's increasing. For a complete graph, it's constant, always 1. So because of that, the path graph, the value, the Wiener index, n cube minus n. Now we can see that this will be, take a graph with n vertices. Either it's a complete graph or path graph with n vertices, fix the n. For path graph, and the distance is more, n cube minus n by 6. For complete graph, the distance is less because always distance between any two vertices is 1. For complete graph, the distance is not 1. Only the neighboring vertices, the distance is 1. So this becomes a lower bound. This becomes the upper bound for any graph. So the two expressions, the lower and upper bound for any connected graph. So there stands the concept, the Wiener index of any graph with n vertices. Lower bound is complete graph, upper bound is the path. So that is for the Wiener index. Similarly, I can think of edge Wiener index. Instead of calculating the vertex distance, I can calculate the edge distance. Edge E1, E2 is 1, E1, E3 is 2, E1, E5 is 2. So calculate the distance between two edges, or that is the distance between two, not atoms, distance between two bonds. Wiener index is distance between two carbon molecules, carbon atoms, two carbon atoms. Okay, that is distance between two vertices, and the edge Wiener index is the distance between two bonds. There is two lines or edges. But can I take the concept of line graph? Yes, I can take this graph, line graph of T. The line graph of T, if you find the Wiener index, that becomes the edge Wiener index of the graph. If it is difficult for us to find the edge Wiener index, find the Wiener index for line graph. And again, a mathematician has a relationship. The edge Wiener index is equal to Wiener index minus NC2 minus NC2. So it was 31. For this answer is 31. NC2 is 15 here because of the number of vertices is 5, 3, 2. So answer is 16. So you can find the H1 and H0. This is a beautiful relationship. Go for the polynomial. Wiener index, you know, the definition for Wiener polynomial. What is Wiener polynomial? The graph is defined as W, G, Q. Q is the variable here. X is Q. It is sigma for all pair of vertices in the Q raised to the power of distance between U. So what is the distance between UV? Neighboring vertices means distance is 1. V1, V2 distance is 1. V2, V3 distance is 1. V3 vertices. So all those possibilities are taken, pair of vertices. Then distance 2, V1, V3 is 2. V2, V4 is 2. V5, V3 is 2. V3, V6 is also 2 because the shortest path is V3, V2, V6, 2. Don't take this way. This is the long, shortest path is distance. Then V1, V5 is 2. And V1, V4 is 3. That's all. So I'll collect all the distances and calculate. So if I calculate W of GQ, the Wiener polynomial, using the formula sigma UV belongs to the Q of dVs. How many possible distance? 3 pair is there. Only one possible. All other pairs have distance 1 and 2. So Q power 3. How many pair of vertices are there with distance 1? 7. 7Q. That means number of edges is 7. That's 7. How many pair of vertices are there with distance 2? 7 pair of vertices are distance 2. So as I mentioned, V1, V3, V1, V5, V4, V6, V5, V4, V3, V6, and V2, V4. So 7 possibilities are there. So if I apply this formula, Q power D UV, it is 7Q square and 1QQ. Because only one possibility is there. V1, V4. Either way you see distance is 3. So only one possible pair is there. For pair UV. So this is called the Wiener polynomial of this particular. Okay, let us use the formula, the Wiener index. What is Wiener index? Start with V1, V2 is 1, V1, V3 is 2, V1, V4 is 3. So 1 plus 2 plus 3 plus 2 plus 2. Then take V2 with the V3, V2 with the V4, V2 with the so on. Then take V3 with V4, V3 with V5, V3. Likewise, I do the calculation. I found that the Wiener index or Wiener number of this particular graph is 24. So this is the calculation. Wiener index is 24. This is the calculation. Wiener polynomial is QQ plus 7Q square plus 7. Now let us have some interesting play with the calculus. Take the Wiener polynomial, differentiate with respect to Q. But differentiate the Wiener polynomial with respect to Q. Q gives me 3Q square. 7Q square gives me 14Q. 7Q becomes 7. So take the Wiener polynomial, differentiate with respect to Q. Okay, W dash Q. Substitute Q equal to 1. Substitute Q equal to 1. 3 plus 14 plus 7. The answer is 24. Substitute Q equal to 1 after differentiation. So that is the derivative of the Wiener polynomial at point Q equal to 1 gives me the Wiener index. Beautiful display. Here we started with the chemical compound, and then we can take a polynomial, we can find the index, and apply here the graph structure. You find the Wiener number, you find the Wiener polynomial, differential calculus comes into the picture. So beautifully things. That is the interplay between the subject inside mathematics. Okay. Then terminal Wiener index. Fine. So why always think the distance between all the carbon atoms? So I am not interested. I want to have the distances between all the terminal carbon atoms, terminal vertices, pendant vertices. So look at a tree. a tree, in a tree, what is the minimum possible pendant index? Two, at least two pendant vertices are there. So I can calculate the distance between two pendant vertices. Suppose you take a path graph, V1 and Vn. The distance between V1 and Vn is n. So thermal index is n. Suppose you take a graph with more than two pendant vertices, plenty of pendant vertices. I take those pendant vertices and calculate the distance between them. Earlier, variance index, calculate the distance between all vertices divided by 2 or sigma d of VAV. Now here, only pendant vertices. See, if you take a chemical compound, in reality, suppose you form a straight, straight chain, okay, not a circuit. So each one puts a chain. I catch the hand of another person, right side I give for another person. Next, my neighbor catches my right hand with his left hand, and his neighbor catches left hand with his right hand. So about 5 people are there, 10 people are there. Other group, the chain grows. But if anybody wants to come and join the chain, which is easy for us, the end person, the first or the last end vertices, can add. But if you want to come and add in between, then you have to break the chain and then keep a distance and again put the chain. So that is better, or the end is better. End is forming the chain, growth of the chain at the end is easy compared to breaking. Already 2 people are holding the hands. You want to break the relationship and then enter into that and form a chain, which is easy. At the end is easy in reality. Similarly, in chemical compounds also, if you have a chemical compound, you want to put a methyl, CH3. CH4 is methane. Some radical, CH3OH or CH3COO, some aldehyde, ketone, acid, anything, CH3 methyl. It wants to enter. Means easy is the end is easy compared to middle. So chemical reactions, breaking the chemical reaction, and in between entering another radical, another chain or single or another compound entering in between or in internal vertices. That's what the concept, internal nodes, terminal nodes. So what happened in 2009, Ivan Gutman, who is still 87 years old in Serbia, Ivan Gutman, he is the editor of the Earth Communication Journal. What happened in 2009, he introduced new molecular descriptor called Tirunelveli index. He says the terminal index is equal to the sum of the distance between all pair of pendant vertices. In particular, Tirunelveli index for a tree is defined. For a tree, it's a sigma dt VAVJ. VAVJ are pendant vertices. In other words, you can say the path number T1E, where the pendant vertices lie on one side of it, and there's no pendant vertices lying on the other side. So calculate only for the pendant vertices. That was having some applications. So here, if you look at this is a tree with 1, 2, 3, 4, 5, 6 vertices on the paths of V1, V2, V3, V4, V6. And then here V7, V8, V9, V10. So 10 vertices are there. You see, these 3 are internal nodes. We have the so how many pendant vertices are there? 1, 2, 3, 4. V1, V2, V3, V4, V5, V6. There are 6 pendant vertices. These are all non-pendant vertices, internal nodes. So let me calculate with V1, V2, V1, V3, V1, V4, V1, V5, V6. Calculations done only for pendant vertices. Then with V2, second bracket, with V3, V4 with V5. So add this 51. 51 is this. What is here? The calculation. So this is how you calculate the terminal vertices. Fine. Then the interest came. Our team, research team, we with the students, we started. We did plenty of other works, but I want to put this one theorem here. Thermal index for full binary tree. What is a full binary tree? Every time it gives two branches for all the levels. It's called full binary tree. So the calculation was very involved here. So just I want to display this. The terminal index of a full binary tree is 2 L power 2 power L minus 1, and the M is equal to 1 to L, M into 2M. So the proof so terminal index of graph G plus. So let me have any compound G. any compounds. So that's the application here. So here as a mathematician, G is an arbitrary graph. What is the terminal variance of G plus? What is G plus? Wherever you have a vertex, you put up and add a pendant edge to it. So original graph V1, V2, V3, Vn. For every vertex, I pull one edge, So I add vertices, new vertices V1 dash, V2 dash, V3 dash, and common edge. So this graph in I think we G1 corona, we can say corona product of G circle dot K1. It's called corona product, or the notation is G plus. I don't want to use the corona word here. I put G plus. So G plus is a graph obtained by any arbitrary graph G by adding pendant edge to each of this. Okay, what is the answer? The answer is very beautiful. It is the P of the G only plus n into n minus 1. Beautiful result is calculation. So where do you apply this? That's the question here. As a mathematician, I am having an idea. Given graph, variance index of the graph is W of G. What is variance index of the graph? W of G plus. W of G plus is W of G plus n into n minus 1. So what is used here? Reality. That means I want to introduce for every carbon atom. Suppose you take a path graph P5. Okay, so that is what is it? Methane, ethane, propane, butane, pentane. Take a pentane. For this pentane, every carbon atom I want to insert on methyl. CH3. That is going to be my P4 plus, P5 plus. So not only path graph, you take a benzene ring. You take any chemical compound, it's such a tree or any graph, to take it, and then the graph for every carbon atom here, I want to put a methane. So the chemical reaction happens, there's a stability. Then what is the thermal variance index of this particular calculation? So that gives thermal variance index of a graph G plus X in the next area. So G plus X is a graph obtained from G by adding G plus, adding an edge from all the interior vertices of G to new vertices. So here what I do is for the graph G plus, I have a G plus already. In G plus again I put one add from an edge from all the interior vertices of G. So here X is a separate vertex, like a parachute joint. That is G plus X I can say. Here what I'm doing is G plus I take and then add to X. So again I have a result here 2p square minus 2p minus. Likewise I have another result. Instead of putting always one methyl, I want to have a long chain compound, tree structures. I take many trees. Okay, joining pendant edge of pendant vertex successively, the terminal vertex of the pth stage. So the compound grows. So there is a provision for me in the reaction that I can have a graph G with k pendant vertices. Graph G with k pendant. For each pendant vertex, these are the pendant vertices. There are graphs V1, V2, V3, V4, V5. But some vertices are pendant, some are non-pendant. For the pendant vertex, V1 is a pendant, V2 is a pendant, Vk is a pendant. What I do is I keep joint vertices. So whenever there is a pendant vertex, easy for me to catch another methyl. So I keep on adding methyls or straight line compounds, and the structure looks like this. Again, it is TW of G is equal to P into K minus. K is the number of pendant vertices. P is the number of vertices. So very excellent derivation result. Then again, look at this. This looks like your case like K1N. So G is a graph with K pendant vertices. I'm not going to corona product. Taking graph G, K pendant vertices are there. V1, V2, V3, Vk like that. There are non-pendant vertices also. Fine. I take the first number for K pendant vertices. V1, Vk plus 1, Vk plus 2, Vk are non-pendant vertices. Fine. That is more than. I draw a graph G dash from G by joining M pendant. So this is right. This pendant vertex V1 dash. I put the pendant vertices, that is V1 dash, V2 dash, V2 dash, and then join this K. That means nothing but here I'm doing this K1 and attach one for all the pendant vertices. So it looks like stars. That is the possibility. So in that case, maybe in reality we don't know whether that is so beautiful is M square T WG. So likewise caterpillar. Caterpillar is a challenging work because take a path, you can put any number of coordinates. So the number of coordinates in the position, how many coordinates in the ith position? That calculation. So these are some chemical compounds, tetramethyl decanate, and there are 4 questions A, B, C, D. So each question I just keep. I have the 12 carbon atoms, straight chain. These 4 in methyl, 4 methyls, decane is 10. I will change position. A molecule structure 3, 4, 6, 10. 4 methyls are put in the position, 3rd, 4th, 6th, 10th. Okay. And then distances are calculated. And then these are the compounds, how the terminal units are ranging. The terminal units are from say 91 to 91, 90. You get a sequence of numbers. Look at the sequence 91, 92, 93. So given chemical compound, I just restructure this position. I am able to get the sequence possible. Okay. So this is the result for caterpillar, and the same terminal index. If you the idea of butyl saturated tree, I will skip this because the time is going. I'll go to the main application. These are also concepts. Similarly, we have plenty of indexes called reverse Wiener index, reciprocal reverse index, reciprocal reverse Wiener index, complementary Wiener index. This is the molecular class 2,2-methyl butane. So we take one compound 2,2-methyl butane and then calculate several indices and plot this value in the graph. This is called energy. I was mentioning that determinant of lambda, the energy. Then the degree-based concept is Zagreb index. I am taking the degree of all the vertices, square it and add it. Let's get Zagreb index. Okay, and then we have the relationship between the index E and Zagreb, and Zagreb. So these are some applications used to quantify the degree of folding of long chain molecules. Provide average centrality of the complex things. Right. So similarly, you can find the Wiener index using Laplacian matrix. Laplacian matrix is V minus A. That A is adjacency matrix, B is degree valence matrix. From this, I subtract, I find the Laplacian matrix. I find the diagonalize it, find the eigenvalues, and reverse the eigenvalues, and multiply by capital N. W is equal to N into sigma I is equal to 2 N 1 by lambda. This is another way of getting. Okay, when I plot the relationship between this e power lambda I, the Suda index and Zagreb index, I get a linear relationship. So these are all certain. So Zagreb index, the definition says that degree square, first Zagreb. Second Zagreb index, the M2 is the product of D of VA, D of VI, and D of VJ. Degree of VA, degree of DI. So same compound earlier we had 24, I think. The graph, this graph, our Wiener index is 18 here. Second graph is 19. So, but Zagreb index definitions are reformulated and so on. This is the chemical compound methylene cyclopropane. Where we have 2 double bonds here. It's unsaturated compound, but still we use this base graph for us to introduce the concept. So this is a compound, very difficult compound. Stability is there. So in reality, this is the existing compound. Fine. So if I look at this benzoic acid, the corresponding molecular graph, and the Wiener index is 42. So that's what I mentioned, that the index of any graph lies between these two lower and upper bound. Fine. This is our own work. It's one for biregular caterpillar. So we have designed this biregular caterpillar. Either degree is 1 or 4. So in this design, we found that this comes out with the general formula 3n square minus 18n square minus 9n plus 2. So this has been calculated by an example here. This is called Hoffman's tree, Pn2, so on. So all these things are interesting result is a degree sequence. You have a graph with at least one vertex of 3 minus 1. The variant index is p square minus p minus 1. The molecular graph of the chemical compound is calculated from the formula. Okay. So likewise, the again some applications, gluing a path to a graph. Okay, that gives me a formula and so on. So gluing rings like cycles, Carnot product with cycles, okay, arbitraries, that gives a formula. So when you look at the molecular structure, biphenyl compound, to take the 2 moles of this, you get this compound. This is done by gluing relationship. And we think of P2 circle dot P6 for for prediction. Okay. So this part I will skip, complementary. Again, number theory applications in what is say the topological analysis. That also I will skip because I don't have time. What I want to say is we can prove certain congruence relation using chemical compounds. Certain chemical compounds gives us the variant index, which are divisible by 12, divisible by 2, divisible by 3. With that help, we can have some congruence. Usually, number theory results are due by induction. Number theory results, certain congruency equations can be proved by the specific chemical structures. That is one application. Fine. So let me come the recent application. Recent means 10 to 15 years before. You know, the discovery of human immunodeficiency virus, HIV. Okay, there's no medicine for HIV, but still there are some medicines which makes the man alive, keep you alive, and it fights. It's an antibiotic. Those medicines are there. Even for diabetics, even for thyroid, there is no curing medicine completely. Only thing is we can make you stand the level. Similarly, this HIV. So how our chemical graph theory is used to predict the quality of the medicine. Okay, see, medicine is there. Okay, main compound of the medicine is just the ratio varies. Depends upon person to person after the test reports. The doctor will change the ratio. Companies will change. The medicine is same. There are 4 or 5 type of medicines. They simply change the ratio. That's mathematics. And then predict which will be better for him when his blood sugar rises to this. It will be better for him once the report comes in. So predicting anti-HIV, polynoculin carbolic acid, an approach of topological. So this is the study here about how medicines are. Analysis of polynyl carbolic acid. Gupta et al. In 2012, they suggested a model using the topological analysis. So look at this compound. This is the structure of the polynyl carbolic acid. Polynyl carboxylic acid. So R is the radical, 2 radicals. Keep changing the compound will be changing the base carboxylic acid. So these are the compounds. For these compounds, we listed out the compound Wiener index, terminal index, first Zagreb index, flat number, Wiener, and we found that the value of this. And then whenever you have minus, it's inactive. Whenever you have plus, it is active. If you look at this, there are pluses. Sometimes there are plus as well as minus. That is both. No reaction. So for various structures, we found the relation and we found the range. And then the report says that based on model, variant index above the range 2009, polynyl carboxylic acid is active. For terminal variant index, depends on the range. Each index. So we have to prepare a chemical in the in the laboratory, drug designer, pharmaceutical laboratory. Every drug cannot be tested. Every drug cannot be tested and wasted time. Some prediction is required. For that prediction, chemical graph theory is not useful. So find the range of the medicine, terminal variant index range, variant index range, see whether it's actively working out or not to sample patients. And then unstability of the compound. Once the compound is stable and is working, such lead compound has been achieved discovery. Yes, I have discovered a useful medicine. This is medicine useful for the people who are in this range. So sometimes for all the 60 compounds which we tested, okay, this has been calculated. Similarly for cancer, prediction of cancer activity for marine, pyridyl alkylates. This is another compound studied in the same way. This is the main basic structure of pyrocriden alkylates. For this, it is all found, the structures we got it from the literature survey, and then we As a mathematics data set comprises 60 components. Okay, calculation of anti-cancer activity. We took the first Zagreb, second Zagreb, and calculated and so for this how it was active or inactive. That's been done. This experimental data is there in the laboratory. With that data, we calculate for the next analysis and therefore investigated, and this has been published long back. I think in 2013. The prediction is available. So, and this portion is a pure graph theory, chemical. So these are the books to be referred. Robbery, a very famous book, chemical graph theory. It's available in National Mathematical Sciences, Chennai, Tirunelveli. Then this is also available in online. Trends Tech, 1930 is very old. It's available, and 1994. This is okay. These are some reference papers along with the research scholars in the university. Where I covered the PowerPoint presentations using our published works. This is the paper, yes, I was mentioning here, 2013 and 2014. We also have a joint work with even Gutman in 2014. But I could not explain this. This is a pure work. And this is in 2015. For deuterosaturated nanotubes and heteromer's. All these things are available in online, free access. Nothing is hidden publication. All my publications are all free to access by the people. I don't do any hidden publications because research is common to all people. Once you publish, it is common for the world. So education is common for everybody. Research is also common. So I'm very open here. And type my name and see. Match Communications, a beautiful journal where Getman is the educator. This is available free access online. Journal of Mathematical Chemistry, Science Director, free access is there. Discrete Applied Mathematics, you know, these are all science directors, and this is one beautiful journal where you can take your picture and enjoy. So I thank all of you for kindly listening in this webinar, this pandemic period. Let us all pray together so soon we come out from this pandemic and the great universe is saved from this COVID-19. Thank you very much, Marthandam. Thank you.
Thank you, sir. It's the time for questions. I think there is one person who has raised his hand, Mr. Gio Solomon. I request him to unmute and ask the question.
Yes.
Hello, sir.
Yes.
Sir, instead of considering multiple...
Can you be a little more louder? You're not audible.
Shaskar.
Hello, sir.
Yes.
Instead of considering multiple edges for double bonds or triple bonds in the unsaturated molecules, in many papers it is considering only simple connected graph.
Yes.
Does this affect the entire physiochemical properties?
Actually, as a mathematics people, we want only the structure and bond, whether it's double, triple, not bother. That's what the concept says. And if you see, there won't be self loops in a chemical compound. There will be only maybe in some places unsaturation will be there. There's no self loop, so the graphs are simple. Earlier itself, I said that we don't consider a single, double, triple bond. Whenever there is a bond between two carbons, we put a line. For us, link is a line. That's what.
Okay, sir. Then, is the characteristic polynomial is applicable only in case of single connected graph?
Characteristic polynomial is
only applicable in single connected graph only?
No, the molecular graph formation itself is only for simple graph. We don't go for pseudo graph or so any type of pseudo graph or multiple graph. We go only for a simple graph. So the concept is only for that.
Okay, sir. Thank you.
Thank you.
Thank you, madam, for the question. Is there any other person who wants to ask a question? If there is any question, you can hand raise. You can use that option in participants, and you can just hand raise, or you can unmute also. And madam, you have a question? And you have a question? No. Is there any other participant? You can unmute, and we'll give you the option to ask your questions, or you can raise your hands. You'll be given. You'll be unmuted. Mr. Mahesh Kumar, you have a question?
Yes, sir.
Yeah.
Good afternoon, sir.
Please go ahead.
I am from.
Yes.
Hello,
go ahead,
sir.
Go ahead. Yes, I can hear. Please. Yeah.
Yeah, I am Kudre from Navi Mumbai. I heard your both the session today. I have one request. Can I give some part of this work as a mini project to my students in engineering?
No problem. In chemical engineering or engineering student?
Mechanical, auto, computer IT, electronics, EXTC.
Computer science students, they can always write algorithm to find the index. For topological index to write algorithm, you can design a programming part. But as a mathematician, writing algorithm and giving the answer in a minute differs from constructing a formula for a family of graph. In that way only, mathematics people, we try to achieve a structure, for each structure a formula. So you can substitute the vertices or number of edges and get the answer. But writing a program and coming out with the answer, that part you can take. That you can do very well. No problem.
Actually, sir, I want to ask one question. That Mumbai University has already included mini project in second year of mathematics subject also.
Okay.
There I can, the syllabus is eigenvalue, eigenvectors, and we are dealing with same structure to some extent.
Yes, exactly.
So if you permit, can I give some part of these
sure.
your research paper to their work?
Very well. Lot of literature is also there. Not only my paper. You can go ahead with finding eigenvalues using MATLAB for big structures. See, 4x4 matrix you have patient to do. If it is a 10x10 matrix, a compound with the protein molecules, definitely go for MATLAB. Go for MATLAB, find the eigenvalues. Then you think of energy of the graph, Estrada index, whatnot index, spectral graph theory. Lot of literature is available. You can give for the students. No doubt.
So that student will get real-time application of mathematics in real life.
Very nice. Exactly. Very good thinking. Yes.
How to approach to you, sir? How to write an
no,
email?
Not in. Go to Google. You just type Wiener index, eigenvalues, application of Wiener index, keywords. You get thousands of papers. Or that math communication journal. You go there, you get plenty of papers available literature. If you type my name, all my papers will come in Google. Free access.
I have one last question. Will you please help us if we require your help, sir?
No harm, sir. Honestly, my website, you can find my mail ID. You can put some questions. I'll answer repeatedly. I'll answer. No doubt. I'll help.
Thank you, sir. Thank you.
Thank you, Mahesh Kumar, sir, for your question. Now I think there is another question from Mr. Jay Kumar.
Yes.
Jay Kumar, sir. I don't know whether he has a question. Vijay, sir, is there any question?
Only one question.
Yeah.
Only one question from Soumya.
Yes, sir.
I will read the question. More papers are used to say indices for drug delivery, anti-cancer agents, and so on, where it is actually applied.
Yeah, anti-cancer or anti-HIV, whatever it is, the drug is used to only defend the disease. How much actively it defends? How much actively this medicine is working? The drug designed, how much it is useful. For predicting that, every time we cannot do some experiments. Sometimes mathematics prediction is useful. That way, the range of the Wiener index or Zagreb index or atom bomb index. Plenty of indices are there. If you go and find out the lower and upper bound value and the medicine, the drug which has the range of particular index in this range is active, keep producing that. Keep for this, keep commands, find out the lead compound which lies in that bound value. That's how our mathematics, especially graph theory, is applicable.
Thank you. I don't know whether there is any other question. If we don't have any other questions, then we'll move ahead to the last part of the program. A vote of thanks. I request the organizing secretary and the head of the research center of the Department of Mathematics, Dr. Vijayan, to propose the formal vote of thanks.
Good evening to you all.
Excuse me, sir. One person, Murugan, has put a question.
Okay.
Is there any other distance applicable for the Wiener index topic? Yes, plenty of distance indices are there. Guttman index is there. Degree distance index. If you go to literature, minute changes are there. Drastic changes are also there in distances. That is for Murugan's question. Thank you. Please continue, sir. Thank you.
Good evening to you all. I'm really very happy to propose vote of thanks on this occasion. First, I thank our correspondent, Advocate Rajathurai, who is a leading lawyer in our district. He's a very good leader and he provides all necessary facilities for the academic improvement of the college. He has also helped a lot to arranging this webinar. I thank you, sir. Next, I thank our principal, Dr. K. Pal Raj, who leads from the front in all academic activities of the college. He only encouraged us to conduct such webinars. So out of his motivation only, we arranged this webinar, a research level webinar for the benefit of the mathematicians in and around or inside in our country. So I thank you, sir. Thank you very much. Next, I thank the Vice Principal, Dr. Vijay, the Bursar, Dr. Jacob Vedaraj, who are also with us in arrangements of this program. Next, I thank the IQAC coordinator who provided all necessary technical help in arranging this program, actually till the end, from the starting to till the end of this program. I thank you very much, sir, for on this occasion. Thank you, sir. Next, I thank the head of the department, Dr. Premla Inbaros, who is one among us in arranging this program. Thank you, madam. Next, I thank the resource persons. First, I thank Dr. John, who is hailing from our locality, a very good mathematician in our locality. Actually, he is very strong in geodetic and Steiner concepts. He has done some original work in these areas. And today also he delivered a very good lecture, and it is useful to all the participants. I thank. He is a well-known mathematician in our state. He visited our institution also to more than 3 occasions for academic purpose. A very good mathematician. He has published many papers in applied mathematics, that is chemical application papers. It is not so easy to do this type of application level research work. He has done it, and he has brought chemistry into graph theory, and he introduced many concepts, and he delivered a very thought-provoking and lecture. Certainly it will help the youngsters to undertake research in this area. I thank you very much, sir. Next, I thank our department colleagues who are always with us in arranging any academic programs, and thank you very much to everybody. Next, I thank the participants. So they actually enthusiastically registered to attend this program, and they have attended till the end of the program. And thank you very much for every participant. And next, I thank everybody related to this program. Thank you very much.
Thank you, Dr. Vijayan, for the vote of thanks for making all these things possible. It is your hard work and the support of the department, the staff members of the Department of Mathematics, the head of the department, and all of the team of the Mathematics department. So on behalf of the IQAC, we extend our gratitude to the department for the wholehearted support, for organizing it in a successful way. Thank you so much. So the feedback link is given in the chat box. The participants may click on the feedback link and fill the feedback so that the certificates could be generated. Again, we would like to tell you that the certificates will be automatically generated. So it may take 1 or 2 days to dispatch the certificates. Kindly be patient. And we also thank the two resource persons once again. On behalf of the IQAC, we extend our gratitude to the resource persons, Dr. John and Dr. Basker sir, for the wonderful session that you have handled today. Thank you so much. Thank you.